Hi, this is lecture 24 of M.3. In last session, we have seen some results about some comparison test given as series AN. We know some ways to check convergence of this series. What are those? There are two with names. One is called the ratio test, the other is called root test. And then we have comparison test. So we have three. So we have three tests as of now. We will do one more test in today's session, and then we will go to the next part. So what was the starting point for to think about ratio test or any root test or comparison test? We are trying to imitate the ideas from the limits of sequences, and we are trying to copy paste here and then see whether we succeed or not. So let us do one more. Let us copy one more thing from sequences, one more result from sequences. What is it? So we are focusing on sequences that goes to 0, that converge to 0. Only then convergence of this makes sense, right? It is not a test, but that is the starting point. If I have a series so that this sequence does not go to 0, then there is no question of looking for convergence of that. It does not converge, that we already know. So now I am focusing on sequences that goes to 0. Now in both in comparison test, at least comparison test, we are looking for other series whose convergence we know, and we are trying to use that the convergence of that series, say summation Bn, n is equal to 1 to infinity. We want to use convergence of this to conclude convergence of this. That is the idea. So we will try to do the same thing, but now let us focus on not this inequality an less than equal to Bn. Let us focus on something else. What is it? We will see now. Suppose I have a sequence. Suppose I have a series summation An whose convergence that I am trying to check. One thing is I can use comparison test. There are series for which this may be too difficult to even imagine what is the appropriate series. Further, we need some other alternative. The alternative is the following. See, in any case we are trying to compare using some other series. What is the first thing for that? We have Bn going to 0. So Bn goes to 0. Now if this is already happening, then An is already going to 0. Suppose this is not happening. Is there other property of sequences such that Bn goes to 0 implies An goes to 0? Do we have that property? That is the first question to ask. To ask yourself, not me. Yes, one of the properties is the following. Suppose, consider the following. Let us assume that An by Bn goes to 1. 1 is not special, any element is fine. Suppose N by Bn goes to 1. Then what happens? We have two sequences that are convergent with the limit being 0, limit being 1. Then we know their product converge to 0 times 1. So in this case what we have is Bn times An by Bn goes to 0. What is this? This is simply An, so An goes to 0. So this is another way to test. So Bn goes to 0 and An by Bn goes to 1. This implies N goes to 0. One is not special here. It can be any element of R. It can be 0 also. That is not an issue. Now once we know that N goes to 0, the next thing to ask ourselves is whether summation N is convergent or not. Let us write down what does it mean to say N by Bn goes to 1. It means given epsilon positive, there is N belongs to N, such that for every N greater than or equal to N, what we have is N by Bn minus 1 is less than epsilon. What is this? This is something as saying An by Bn is less than epsilon plus 1. We have other inequality here also. Let us put that. This is what 1 minus epsilon less than an by bn less than epsilon plus 1. Now what? An is less than epsilon plus 1 times bn. So for every n greater than or equal to n. Now suppose I am trying to apply that I know this bn is convergent. Suppose I assume that an is non-negative, an is greater than or equal to 0, then I can just simply put 0 here, and now I can use comparison test. With what? I can use comparison test with respect to not bn but epsilon plus 1 times bn, because we do not have an less than or equal to bn. What we have is an less than or equal to epsilon plus 1 times bn. How can I use that? Summation bn n is equal to 1 to infinity is convergent. This implies summation n is equal to capital N to infinity bn is convergent, which further imply I am just multiplying that by some other element, is convergent. Now what? I have a sequence such that this is less than or equal to this, and we know this is convergent. Same comparison test says n is the summation an n is equal to n to infinity is convergent. Again we know already. Suppose I know that some series is convergent from excluding a few terms in the beginning, I can extend that idea to the series starting from 1. Right. So what did we achieve now? Suppose we have a series summation bn. Suppose we have a series summation an whose convergence we are trying to check, and we are not in a position to apply comparison test. The other thing, that the next best thing that we can do is use this idea. Look for a series whose convergence that you already know, then make sure that n by bn goes to 1 or any other element. It can be 0 also, not a problem. It can be an element of R, it should be convergent, that is the only thing. Then what? Then with the justification that I have given just now, it concludes that summation bn is convergent. One can slightly change this idea to include absolute convergence also. Here we got convergence, we can get absolute convergence also. Now suppose we did not get this, what we get is something different. So this is one test whose we will do one example for that, then it will be clear what is happening here. So let us do some example. So now we are given some series whose convergence we are trying to check, and then we should first of all guess a series whose convergence we know, and those two should be related in this sense, so to some other element. Consider the following series: summation 2 power k plus k by 3 power k minus k. See, there are many other ways to check convergence of this, but we are trying to use the previous idea that we should look for a series that is convergent, and this fraction should go to 1 or any other number. As I said, 1 is not special here, if you can observe. See, I can replace 1 with anything. This is just a constant, right? So now the question is just like in the case of convergence. Suppose I give some sequence and I have to check convergence. The first thing is you need to look for appropriate number, then check the convergence of that. Here also it is the same issue. Now the problem is with looking for a series that is convergent, n is equal to 1 to infinity. Let me change this also to n, writing as k here. Let me change everything. 2 power n plus n by 3 power n minus n. Now we are trying to see whether we can get a series such that this by bn goes to 1. Now one series, see we only know very few series which are convergent. One of them is we know 1 by n square, or the same thing can be extended to 1 by n power k also for any arbitrary k not equal to 1. Then we know 1 by n factorial is summation 1 by n factorial is convergent. Then we know some few similar series. One of that is the following: summation L power n is equal to 1 to infinity is convergent whenever L is less than 1. What is the relevance here? Observe that we have 2 by 3 with some power and all, but ideally this should be seen as something to do with 2 by 3. Let us check. See, we know that summation 2 by 3 power n is convergent. Let us check if this by this is going to 1 or not. So 2 power n plus n by 3 power n plus 1 whole divided by 2 by 3 power n, that is same thing as 3 power n by 2 power n, right. So this I am seeing as the following. This is so I am just trying to divide this by this and this by this. Oh, this is not plus 1, this is minus n, this is minus n. So now what I have is, I have 1 plus n by 2 power n by 3 power n is 1 minus n by 3 power n. Now what? You should have done this example before. This sequence goes to 0. Similarly, this sequence also goes to 0. What about the whole sequence? This will go to 1. 1 plus this limit is 0. 1 minus this limit is 0. 1 minus 0 is 1. 1 plus 0 is 1. So this goes to 1. So now what we have is, we didn't really do much computation here. All we have done is we have looked for a series that is convergent, and this by this goes to 1. So as I said, this limit comparison test, this a n by b n going to 1 or any other element, this will be useful when in the given series you have a fraction like this. It may not work every time, of course. if it is a fraction like this, then you can look for other fraction. So this comparison test, limit comparison test, is useful when you are dealing with the series whose terms are fractions of this form. Then we can use other series that is also fraction. One first guess should be something like that, that summation n is equal to infinity L power n, where L is less than 1. You can take 2 by 3, 3 by 4, 1 by n, whatever it, 1 by 4, something like that, and try to compare with this and say the corresponding ratio goes to 1 or any other element. So this is one thing. Now maybe I will do some more examples I will mention some more examples in the lecture notes. Now let us focus on another interesting series that we are calling as a power series. Not me, in general it is called as power series. So what's a power series? A series summation bn is equal to 1 to infinity. This is the usual notation for the series. Now suppose the elements of this are of the form, see bn can be one special kind of sequence. This bn is a sequence that comes from other series, a sequence an and fixed element of r. So let me write down that bn is equal to an h power n, n belongs to n. Series summation 1 to infinity bn, where bn is of the form n x power n, is called a power series, or you can directly write this an x power n, n is equal to 1 to infinity. This is what is called a power series. So let us focus for now on convergence of series of this form. Okay, so now let us focus on convergence of series of this form, the power series. So observe that this has two parts, one is some arbitrary sequence, then this other part is coming from a single number, that is the speciality of this power series. So before we proceed further, one simple question to ask is, suppose I know that summation an is convergent, do I know that this corresponding power series an x power n is convergent? Do we know that? I mean, is it fair enough to expect something like that? That is the question. See, this thing, it looks like it depends only on convergence of an. So I am assuming it is convergent. Then can I say for sure that for any x this is convergent? That is the question that we are trying to ask. So let us check whether an x power n is at least going to 0 whenever n goes to 0. This is the first question to ask. Forget about convergence of the series. This kind of thing you might have seen. I think I have mentioned in the portion of sequences of real numbers. Okay, so let us look at the following example. Let us take a sequence that goes to 0 and let us check whether this thing goes to 0 or not. So one example of sequence that goes to 0 is 1 by n. 1 by n goes to 0. Now what you are asking is it true that for any x, an x power n goes to 0? Let us take x is equal to, if I take x is equal to 1, there is nothing really, so let us take x is equal to 2. So for x is equal to 2, what is x power n? That is 2 power n. Do we know if 2 power n by n goes to 0? This thing is not even convergent, forget about converging to 0, it is not even convergent. So asking for this convergence implies this convergence is too much. It does not even goes to 0. See, this is the first step to proceed here, right? Here itself we are it failing, even though n goes to 0, and even if it is convergent. Okay, one can ask, here I am taking the this thing 1 by n, but summation 1 by n is divergent. Maybe that is why it is not going to 0. We can take n square also. What is the problem? N square, summation 1 by n square is convergent, we have seen in the last session. Then the same thing, 2 power n by n square, this thing is not convergent, forget about converging to 0, it is not convergent. So one cannot really say that summation n being convergent implies this. So first thing to do is the following. Let us first look at some result that says it is even going to 0 at least. What is the result? Suppose I know that I have a sequence Bn and it is bounded. Suppose Bn is a sequence and it is bounded, then if An is going to 0, then An Bn will go to 0. How do I know that? Exercise. Check for yourself. See, this was the problem with when we are dealing with 2n. 2n is unbounded, so this is not a counterexample for that anything. So you take any bounded sequence and any sequence that goes to 0, then their product goes to 0. So then one can talk about the corresponding convergence of the series, summation an and bn n is equal to 1 to infinity. So in this case bn is x power n. I said we are dealing with power series, right. See, all we are trying to do is the following. We are starting with summation an, this series, most likely this should be convergent, and then we are trying to see whether this is convergent or not. As I said in the first observation, it is necessary that this sequence is convergent, x power n is bounded, convergence is maybe too much to ask, it is bounded. Now, do we have an example of sequences that are of this form, L power n and bounded? One example that we know is whenever x is less than 1, minus 1 x less than 1. This is one place where I know for sure that x power n is bounded, it is bounded by 1. Now, is it true that if summation n is convergent, can we say anything about this? Now, let us assume that x is positive, that 0 less than x less than 1. Now, let us try to compare this with this. An x is less than 1, so x power n is less than or equal to 1. An x power n less than or equal to an. For this to, if you have to write something like this, I should know that an is non-negative. Let us assume for now that n is non-negative, then it implies this. Again this implies what? 0 less than or equal to this. Same comparison test. I know that this is convergent, this implies this is convergent. Maybe from, yeah, this is convergent. Now one can get rid of this thing by asking that n is absolutely convergent. So, so again the same thing, x is positive, so x power n is less than or equal to 1. Then we are not asking that n is non-negative. What I know is changing the starting point. Instead of asking that this is convergent, I am asking this to be absolutely convergent. Then what is the nice thing that is happening here? I can multiply both sides. Here I multiplied both sides by assuming n is non-negative. I can multiply both sides here by assuming that an, instead of n I am doing mod an. Right, mod n is already non-negative, so I can do that. Now what happens? I have two sequences with the property that bn less than or equal to an for every n belongs to n, everything is positive. I said x is positive. So this imply, again same comparison test, this imply that summation an x power n is absolutely convergent. See, I can actually put mod here also, it does not change anything because x is positive. So I can put mod, and this still holds. So this says this is absolutely convergent, and absolutely convergence implies convergence. So this thing is convergent. Now one can make it much better. Previously we are assuming that n is non-negative, so we are assuming two things. First thing is that x is positive and n is positive. We are assuming two things. Then we have x power n less than or equal to 1. Then because this is because x is positive, I will assume that x is positive, that's why we got this. So n is non-negative, so we multiplied both sides by an. Then we use comparison test to conclude that because this is also non-negative, we use comparison test to conclude that summation an x power n is convergent. Now we have got rid of this. We don't want to ask this. Instead, we are asking that summation n equal to infinity n is absolutely convergent. What does it help? That will help us to, that will allow us to multiply both sides of this inequality x power n is less than or equal to 1 by mod an. Then again same comparison test will conclude that summation an x power n is absolutely convergent. Absolute convergence plus convergence. So one can one see that this is a convergence. Now one can also relax this condition that x is positive, but this is necessary. Absolute convergence is necessary. If I relax x is positive, then what I have to do is I have to say mod x is less than or equal to 1, mod x power n is less than or equal to 1, but if I have to put 0 here, I should know that it is, what I am writing here is positive. If I don't take this mod, then I cannot. Then I am already assuming that x is non-negative. So if I allow to relax this condition, then I am changing the starting point. Instead of taking x, I am taking mod x. Now again for this, do the same thing. Multiply by mod n on both sides. That says mod n x power n is convergent. That means summation n x power n is absolute convergence, which implies convergence. So one can get rid of this and this, but one should ask it's absolute convergence. So let us combine all that and write down. Suppose I have a series summation an 1 to infinity is absolutely convergent and mod x is less than 1, then summation an x power n is convergent. This is one result. So this says some result about this series, is concluding something about it's useful to conclude something about this series, the power series. Now we want to get rid of this absolute convergence also. This is also too much for many. Sometimes we know some example, right? Summation what was the example? Minus power n by n. this is convergent but not absolutely convergent. So I want to get rid of this absolute convergence also. So what do we do? Let us try the following. Mod x is less than 1. Instead of starting at convergence of this part, let us focus on convergence of this part. So convergence of this part is what we are focusing on, right? Let us focus on convergence of this part, summation x power n. So this is less than 1 implies summation mod x power n is convergent. Now I am relaxing this condition of absolute convergence. I am assuming it is only convergent. So what does this mean? In particular, this means n goes to 0. Right, that is only that we are using. This means given epsilon positive, there is n belongs to n, such that mod a n is less than epsilon for every n greater than or equal to n. Some of you might be guessing already what I am going to do. So this is true for any epsilon positive. One can take epsilon to be 1, or I will just write epsilon is equal to 1. So here it is less than 1. Now what? Mod a n less than 1 after some n. I am multiplying both sides by this is both sides by xn. It is positive. Now what? We have a sequence a n x power n that is bounded by the sequence x power n with modulus, of course. Same comparison test, 0 less than or equal to this, that says a n x power n modulus is convergent. That means what? A n x power n summation is absolute convergence plus convergence. So this thing is convergent. So what we have done is we have even got rid of this absolute convergence condition also. So now what we have is, suppose we have a series summation a n that is convergent, then for any x with mod x less than 1, this thing is convergent. If you observe carefully, we did not really use that it is convergent. All I have used is that this thing goes to 0. We have some example where this goes to 0, but this is not convergent. What is it? 1 by n. And if you ask more than that, all I have used is I have simply asked that a n is bounded. Right? There is a here it is after a certain n, but that is sufficient. That if n is bounded, then there is some element m, so that n is less than or equal to m for every n belongs to n, or this is also sufficient. Then I can just put m here. If xn is bounded, xn is convergent, then mxn is also convergent. So this so we have this. So now what does it say? Checking for convergence of power series a n x power n 1 is equal to 1 to infinity. This thing, it is most likely that it is convergent if I know that mod x is less than 1 and a n goes to 0. Boundedness is also sufficient. Now we are trying to, we used convergence of the series summation a n to conclude convergence of this series. Now let us fix some element x belongs to R such that summation a n x power n is convergent. Now let us take other series summation 1 to infinity a n, we call this x0 is the fixed point like that, x power n. Previously, see observe what summation n is equal to infinity a n convergence implied something about for some arbitrary x with mod x less than 1. Now we are putting something here x0 something like that. So then 1 was mentioned here, 1 is mentioned here. So maybe it is true if I put some say x power n here, I should put x power n here also, maybe 0, x power 0. maybe the power also should change. Okay, what I am going to say is the following. Suppose I have x0 belongs to R such that this is convergent. Then if I take any x such that mod x is less than mod x0, see previously x0 was 1, right? This was not there, we are trying to conclude about convergence of this. Now there is x0, so then I have to ask this condition. Previously it was mod x less than 1, so now it is this. Now how do I proceed here? Same idea. Mod x less than mod x0 implies what? X by x0 power n, it goes to 0. So summation x by x power n, x by x0 power n is convergent. Now again this is convergent, which means what in particular, that this is going to 0. So again the same trick, that given epsilon positive, this converges to 0 means what, there is n belongs to n such that a n x0 power n is less than epsilon. Again take epsilon to be 1. Now we are trying to, starting from here, we are trying to somehow reach a n x power n. So now what we are doing is we are trying to compare this n x0 power n with this. So further we need a trick. The trick is the following. We write a n x power n in terms of a n x0 power n, but these are not same, of course, right? There is x here, there is x0 power n here. So what we will do is we will multiply and divide by x power n, x0 power n. These two get cancelled, then these two are same. Now what? This thing is less than or equal to 1, right? And okay, this is less than or equal to 1. So if I put mod here, this is less than or equal to, or maybe less than, this part is 1. So this I am leaving as it is, x power n by x0 power n. Now again same comparison test. I have a series such that each term is bounded by, see, elements of this series are bounded by elements of this series. This I know is convergent, that implies this is convergent. This is absolute convergence, but then again absolute convergence implies convergence. So that says summation a n x power n is convergent. So what we need to observe here is the following. Suppose I have a series summation a n x power n. Suppose I know that for some element of x this is convergent, this whole thing is convergent, then suppose it is x0, then what we know is for any x with mod x less than mod x0, summation a n x power n is convergent, absolute convergence anyways. Yes, so that is about the convergence of power series. Once I have a sequence a n and if there is some element x so that this is convergent, then for any x with this property, this thing is absolute convergence. So this is where we talk about notion of radius of convergence for a radius of convergence for a power series. More details I will add in the lecture notes. But this I am saying, this is not part of the syllabus, but this I am saying so that it will be useful to when you read something about a Taylor series or something like that. So yeah, now what we have done today is the power series. Of course we have done that. Then we have said that including the ratio, root and comparison test, we talk about other test, the limit comparison test. Now we will do some examples. Summation 2 power n plus n by 3 power n plus n is 1 to infinity. Now see, this is a series of non-negative terms. First thing that we can do, we can use comparison test. See, whenever I see something like 2 power n by 3 power n, I will be thinking about the series summation 2 by 3 power n, which I know is convergent. So I will try to use that in the comparison test. So first thing to do is let us check if this is true. 3 power n plus n less than or equal to 2 power n by 3 power n. Is it true? It's not very clear whether it is true or not, because in the numerator there seems to be some problem. This is fine. 3 power n plus 1 is 3 power n plus n greater than or equal to 3 power n. This implies 1 by 3 power n plus n less than or equal to 1 by 3 power n. So this part is fine. The only thing is I am adding some element n here. So can I do that? That's not very clear whether it is true or not. So what we do is we will not write like this. We will change it slightly. 2 power n plus n, 3 power n plus n. Let us leave it as it is. This part let us leave as it is. Let us change only this. So that is less than or equal to 2 power n plus n by 3 power n. Now this is less than or equal to 2 by 3 power n plus n by 3 power n. Now the other problem is I need to check convergence of two series now, because I don't know convergence of this series yet. So what we will do is we will change this also. How to change, it's not very clear, but one obvious choice is the following: n is less than or equal to 2 power n, right? If n is equal to 2, 3, whatever you can check, less than or equal to 2 power n. So let us just write that 2 power n by 3 power n plus 2 power n by 3 power n. This is how much? 2 times 2 by 3 power n. Okay, this seems to be correct. We cannot get this, but we can get some multiple of that. 2 power n plus n by 3 power n plus 1 less than or equal to 2 times that. See, it's okay, something is close to this. This much I know. Summation 2 by 3 power n is coming, this much I know. If I multiply this by 2, that's also okay. I already mentioned, suppose I take a series, if I multiply the whole series by one element, then the resulting is still converges to 2 times the previous series. So this is fine. So I can just use this inequality to conclude that this series is convergent. Okay. Let us do one more example. It was very easy. Previous example was very easy. Let us do one more example. So previously we said that some sequence doesn't go to 0. So consider the following example: summation 1 to infinity 2 power n by n factorial. What we know is this much is convergent. Summation n equal to infinity 1 by n factorial is convergent. This much we know. Now we have some extra term 2 power n here. Let us check if this is convergent or not. What I know is, as I said, whenever I see 2 power n by 3 power n, something like that, then I will think of just 2 power 3 power n. Then I will try to estimate this with that. Let us see if it is possible here also. Do I have that n factorial is greater than or equal to 3 power n for every n belongs to n? This is the case. Then 1 by n factorial is less than or equal to 1 by 3 power n, and 2 power n I am writing as it is. Then what? Again I use same comparison test to conclude that from here and convergence of this, we conclude convergence of this series. Now the first thing to do is, let us check whether this is true or not. Let us do one at a time. For n is equal to 1, what we have is 1 factorial is 1, 3 power 1 is 3, greater than or equal to 3, sorry, n is equal to 2, 2 factorial is 2, 3 square is 9, no, what about 3, n is equal to 3, 3 factorial is 3 to the 6, 6 greater than or equal to 3 power 3 is 3 3 is 9, 9 3 is 27, no, maybe it is not true. Let us do some more and then see. N is equal to 4. I am just copy pasting this here so that I don't have to go back there again and again. So n is equal to 4, 6 4 are 24, 24 greater than or equal to I am lost. What is 3 times 27? 3 7s are 21, 3 2s are I don't know what is it. 81. Not true. What about 5? 5 factorial 5 times 24 is 5 4s are 20, 25 2s are 120. It doesn't seem to be working. Let us not give up. There is a reason why I am not giving up. I am multiplying this by 6 and this by 3. 0, 6 to the 12, 7, 20. 3 3s 9, 3 4s 12, 3 2 6. Okay, there seem to be some. See, this is of course not true, there is no doubt about it, but look at the error. The difference between this and this is something around 100, more than 100, and this is the only 9. Let us do one more. N is equal to 7. What I am doing is I am multiplying this thing by 7 and this thing by 3. It's slightly difficult to do here, but let us do. 0, 7 2s are 14, 7 7s 49, 50. Multiplying this by 3, 3 9s are 27, 3 2s are 6, 8. Oh my god, this is true. From here, in the next steps, whatever I am going to do is I am multiplying this side by number greater than 7, but I am multiplying this side by number equal to 3 every time. So the inequality will still remain. Only till here there is a problem. Till n is equal to 6 there is an issue. From n is equal to 7, see this is true. Afterwards also what I am doing is I am multiplying left side by element that is greater than 7, on the right hand side by element 3 every time. So this says what? N factorial greater than or equal to 3 power n for every n greater than or equal to 7. So this is not true. So this thing is not true from 1, it is true from n greater than or equal to 7. So now what? So till then I can apply, from then I can apply comparison test and then conclude summation 2 power n by n factorial n is equal to 7 to infinity is convergent. Again what? I can just apply, write down the first 6 terms, add it up, then this imply summation n is equal to 1 to infinity 2 power n by n factorial is convergent. So the lesson that we should learn from here is the following. Maybe sometimes your guess may be correct, but it may be correct, it may not be completely correct from the beginning, but if you skip some steps after that it may be correct. Here we are stopping at 7, maybe there are, maybe if your estimate is not really nice, it may be true from n is equal to 59. How do I guess that? You cannot really do anything about it, you just have to, depending on the behavior. See, if because I see some hope here, the difference has reduced from 100 to 9. So I am assuming that in the next step I'll reach somewhere. So if there is some hope, then you proceed further. If there is no hope, then you can just leave it and then look for other alternative. So these are the examples. We have done 2 examples and 1 test, then something about power series. Then I mentioned about radius of convergence. This I will add in the lecture notes. Right here it is radius of convergence. This I will mention in the lecture notes. Okay, there is one more thing which I am not saying here because of time constraint. There is something called rearrangement of series. What does it mean? Suppose I have a series summation an is equal to 1 to infinity. Suppose I know that this is convergent, then all I am asking is the following: See how does a series, how does sequence look like? It's a map from N to R, right? It is some map from N to R. Now what I am asking is, I am composing this sequence with a bijection from N to N, let us call this F. Then I am considering the corresponding sequence A, compose F from N to R. This is other sequence. Now what I am asking is, do I know that summation 1 to infinity A Fn, is it convergent or not? This is what I am trying to ask. So this I will mention in the lecture notes. There I also mention some example where this is not really happening. Then you will realize that what is the necessity of thinking about this case. So as I said, this is called rearrangement of series, and that's all for this section about series of real numbers, summable sequences. In the next session we will start doing integration of functions. That's all.